chapters 10 and 11 are focusing on hypothesis testing. And hypothesis testing is probably one of the more intriguing topics that we'll talk about in the class. It builds on much of what we've looked at in the past several chapters. I think section 10.1 is extremely useful, and I'd recommend you study it with care. It walks us through the steps of a hypothesis test. What we're essentially trying to do with hypothesis testing is to test a claim and then use the data available to either support that claim or reject that claim. The most fundamental aspects of hypothesis tests are going to be our null and alternate hypothesis. Our alternate hypothesis is also sometimes referred to as the research hypothesis, and that's going to be what we're testing the data for. The null hypothesis, by definition, is going to make the opposite claim, or initially argue that a value is either equal to something, equal to a certain value, or effectively the opposite of what the alternate or research hypothesis is claiming. When I was coming up through and taking statistics courses, the null hypothesis was just about in every case with an equal sign, mu equals some value. More recently, textbooks are now evolving to where they're using an inequality, either less than equal to or greater than or equal to some value, and then your alternate hypothesis is taking on the claim or the question, which is then the opposite. So understanding the null and the alternative are important. As we go through each of the tests will then test a specific claim based on the whatever the data that's presented to us, whether we have a known standard deviation, an unknown standard deviation, and so forth, somewhat similar to chapter 9. Also, there's going to be certain errors involved in the testing, and we can talk about statistically significant results. So we're going to use alpha to refer to our level of significance. We're going to be dealing with typically 1% or 5% alpha levels. So if alpha is equal to 1%, then that's a 1% possible error in our test. If alpha is equal to 5%, then that's a 5% level of error built into our test. And then it also has to do, it's related to the level of confidence within our test. So 1 minus the confidence value always equals alpha. So if we're using a 95% level of confidence, then that means that the error has to be 5%. If we're using a 99% level of confidence, then the error has to be 1%, and so forth. And we're trying to effectively use the data to prove the claim within a certain confidence level that has degrees of error. Now, at the end of our test, we're either going to do one of two things. We're either going to reject the null hypothesis, or we're going to fail to reject the null hypothesis. We're not necessarily in the business of, quote, proving any claim, or it's very difficult in statistics to come up with some absolute proof. So we're using what the philosopher of science Karl Popper referred to years ago as the process of falsification. We're effectively trying to falsify the data and then look somewhere else. If we cannot falsify the data, and therefore we fail to reject the null hypothesis, then we're going to say that we hold on to or keep the alternative or research hypothesis at least till a time in the future in which we can potentially falsify it. 597 talks about how to proceed through the steps of the hypothesis test, state the null and alternative hypothesis, determine the distribution used for the test, and that depends upon the data given to us, whether we use a z, a t, chi-squared, f distribution. And we need to know the level of significance or the error, which also gives us the confidence level. We gather the data, calculate the statistics, and then based on that, we're either going to be able to reject or not reject the claim, and then we'll draw conclusions and make some decision about what our test has been able to say to us. Two other very important items still in 10.1 is the concepts of type 1 and type 2 errors. And pages 598 and 599 are particularly interesting and important. Talks about types of errors in hypothesis testing. If we're talking about, again, we can either effectively um, make a couple types of errors. We can either reject a true null hypothesis, which would be a type 1 error, or we can fail to reject a false null hypothesis, which would be a type 2 error. And when we talk about alpha, the level of significance, alpha is effectively the probability of making a type 1 error, rejecting a true null hypothesis. When we talk about fail to reject a false null hypothesis, a type 2 error, we're going to call that beta. And beta is the probability of making that type 2 error. And those pages are pretty clear, and you need to really understand the conceptual difference between alpha and beta probabilities of type 1 and type 2 errors. Okay, the chapter goes ahead and it effectively walks us through 10.2 walks us through hypothesis testing for population mean with sigma known. There again, we expect the sample size to be greater than 30, so we are going to use the z distribution for that. And it walks us through the z-test, and whether we use also, it's important, whether we're going to have a one-tailed or two-tailed test is also important, which is going to help us determine our critical values, in this case our critical z-value, to determine the rejection region, which our test statistic then is based upon. We measure the test statistic that we calculate against the critical, in this case z-value, whether we're then going to reject or not reject, or fail to reject the null. And again, the text and the Hawks Learning Program are very good at walking you through that and describing the process. Also, let me mention that the p-values are incredibly important. We have to be sure we're comfortable with calculating p-values as we go through. P-values are the probability of obtaining a sample statistic more extreme than the observed data when the null hypothesis is assumed to be true. So it's the probability effectively of rejecting our claim, and p-values are in fact important. When we calculate p-values, the general rule is that if we have a very, very low p-value, then we can in fact reject the null hypothesis. If we have a very high p-value, then we typically fail to reject the null hypothesis. So it's important oftentimes to be able to understand and comprehend the meaning and the purpose of p-values as we go through. Okay, so as I said before, if our p-value is low, and by low I mean less than alpha probability of the type 1 error, then we reject the null. If the p-value is high or p-value is greater than alpha, then we fail to reject the null hypothesis. Those are just rules of thumb, but remember our alpha will change as our level of significance depending upon whatever confidence level we choose. Typically 99-95% confidence, which translate into 5% or maybe 1% error. Some tests may use a 90% confidence interval with a 10% error. That may not tell us as much as we would like, but actually confidence intervals and alphas can be anything. They can be any values that we choose or error that we like. As we get into 10.2, again, very similar type test, except now sigma is going to be unknown. And when sigma is unknown, we're going to have to step back and use our t-test. 10.4, it gets into hypothesis testing for proportions, which is again back to the z table and the z-test. We also have hypothesis testing for population variances, which does use, in this case, the chi-squared values, and I'll walk you through that. Then in 10.6, it separates out our very own chi-squared test, which is a goodness of fit test, which also is important in certain applications, and you'll be able to see those. And then 10.7 is again another chi-squared test for association, and it is also very useful in certain situations. And once you get into Chapter 11, you're going to be able to see that it's still talking about hypothesis testing, the same concepts, except now we're talking about 2 or more populations, and you go through essentially the same dynamics as we mentioned before, except now we're comparing 2 sets of data instead of 1. The formulas changed slightly, but it's still the same concepts. But another tier is added. So if you understand Chapter 10, you should fairly easily understand Chapter 11 as well. It's all hypothesis testing. Again, I do encourage you to use your graphing calculator. All these tests can be performed. If you have the TI-83 or TI-84, I have the TI-84 Plus, which is particularly a good device to use. But again, hypothesis testing is a critical piece of the course. These are 2 chapters. Oh, and let me also mention, once you get over into 11.6, you do get into ANOVA's, analysis of variance, which then allows you to compare the means of 3 or more populations. So you get multiple data sets. And as you move up into higher level courses that are using lots of types of research, whether it's in business, whether it's in nursing, whether it's in the social sciences, or science in general, the ANOVA test for research purposes is incredibly important and is widespread in published journals, published research. The ANOVA test is an important test to understand, and it's just, again, building on the general concept of hypothesis testing. So pay close attention there when you get into 10.6. Okay, so that gets us through chapters 10 and 11. I hope you're diligent working through those, not getting frustrated. Again, I recommend to read the chapters, go work through the Hawks program homework, come back to the chapters, work some problems out of each section, review it, study it, and then go back and work the individual quizzes for 10 and 11, which will culminate obviously with the 3rd exam that's coming up in December. So again, I hope you enjoy working through hypothesis testing. It's a critical piece of any academic career if you're going to be engaging in research down the road. Please let me know if you have any comments or questions. And I hope you have a happy Thanksgiving if you get to watch this before then.